Hello students, I am Anup Kumar Kapoor from Department of Anthropology, University of Delhi, Delhi. Today I am going to speak on the module Skeleton Analysis and Determination of Demographic Variables in Prehistoric Populations from the paper Human Origin and Evolution. The learning outcomes of the modules are: first, from this content, one shall be able to know about the skeleton analysis and determination of demographic variables in prehistoric populations. First of all, we will discuss briefly about human skeleton in the light of skeleton analysis. The human skeleton proves to be an extremely valuable source for the reconstruction of past life parameters due to its resistance to decomposition. Archaeologists, historians, and anthropologists alike rely on these biological building blocks for many paleodemographic inferences, and, not surprisingly, there is a long-standing tradition of establishing mortality profiles from prehistoric cemetery populations. These death structures serve as indicators of over life expectancy, fertility, and even population growth. Moreover, historical patterns of health, disease, and ontogenesis are used to isolate biological as well as social life history factors. Mean age at death of this population was about 35 years, with some individuals having survived till 50 years. The prehistoric sample displays complex biological variation, and evolution of prehistoric inhabitants possessed general skeleton biology, facilitates synthetic review of biological temporal trends, and suggests a general temporal increase in certain pathological conditions and other indicators of population status. First is skeleton analysis. Now, the demographic study of a skeleton sample begins with the assessment of both the age at death and sex distribution of the skeleton material. These data are absolutely essential for the construction of other population statistics. Second is assessment of age for the fetus and the young infant. Forensic dentists, through the utilization of X-rays, can reasonably estimate age from 13 to 16 weeks in utero through 14 years of age, when classification of the permanent second molar usually occurs. An understanding of the time of appearance of major ossification centers is very helpful in the determination of skeleton age in the child and young adult. The appearance of ossification centers is typically completed around 5 years of age. From the period of 5 years of age up to approximately 25 years of age, the fusion of the epiphyses is utilized for age determination. When determining the age of skeleton remains, the important points are: the first is the age of skeleton remains are affected by sex, race, and nutrition of the deceased. Also, maturity of the disease is not synonymous with the calendar age. Second, female skeleton remains are almost always in advance of males of the same age, race, nutrition level, and geographical location. Maturity tends to be more advanced in those who live in the hotter climates. Third is, there are substantive variations in epiphyseal closure dates. Epiphyseal union occurs over a period of time and not at all at once. As an example, epiphyseal union of the medial end of the clavicle occurs typically over a period of time ranging from 18 to 30 years. examination of epiphyseal closure of long bones is used for the determination of the age of skeleton remains extending from mid-teens to the early 20s. The skeleton aging in the later years is not nearly as finite as skeletal aging in the child and the young adult. From 25 years until old age, there are no dramatic events such as tooth eruption or the appearance of ossification centers. There are three anatomical structures which are used in this period of life. For aging, the pubic symphysis, sternal ribs, and skull sutures. The right and the left hip bones, what we also call innominate bones, meet in the midline in front to form the pubic symphysis. It should be understood the right and the left pubic bones do not actually articulate. They are separated throughout life by the symphysial cartilage. Each pubic bone presents a symphysial surface or face. The second is the age determination through skull. Age determination can be accomplished through as follows. Metopic suture closes at 2 to 4 years, sagittal sutures 30 to 40 years, coronal suture 40 to 50 years, lambdoid sutures 40 to 50 years, sphenotemporal suture 50 to 60 years, parietomystadal sutures 80 to 90 years, masto-occipital suture 80 to 90 years, squamous sutures above 80 years, basal suture fused by 18 to 20 years. Now I will tell you how or where the sutures are placed on the human skull. This is the human adult skull of male. Now, to determine the suture, first we should know the different part of the human skull. When we see, this is the frontal bone, this is the parietal bone, and this is the occipital bone. That is the three important points, but there are other points. Then we have a zygomatic arches, the orbits, and the maxilla. But when we come to the aging of skull, there are certain sutures I told you earlier. The first one is the metopic suture. It is, now we see this is the forehead. And this is the metopic point. Though in case you have done in anthropometry, there is a metopin point. These metopin point represent the metopic suture. Now here, this metopic suture is present here, but that is fused on the skull at the age of 2 years. Means this is the first suture on the human skull which fuses at the age of 2 years. Then, now when after 2 years, the suture fuses, right? Now, the second suture comes, now we say there are three important sutures. That is the coronal sutures here, that is the sagittal sutures, in where the two parietal bones are meeting, and then we have on the occipital bone we have lambdoid suture. There are two sides, right side and the left side. Means here the parietal and the occipital bone, they are fused together by these sutures. Now the best example of the suture is when you go to a tailor. So you go for a stitching of the shirt. How he carry out the stitching? He used the machine or a hand, he used the needle. So means here, that is the same concept. The sutures are fusing together two bones. And these sutures, they are fused in different time. For example, the coronal sutures. Now, there are certain important points. The sutures start fusing from the center of the suture. Now this is the coronal suture. We take the central point for the fusion or obliteration of sutures. From here it will go. Now it is not possible to explain everything, but for a general purpose, when we take the one point, that is the crinometric landmark, that is the bregma, to the last point, we divide these sutures into 3 or 4 equal parts and then we measure it. and we start the measuring from the central portion of the suture. So this suture, all the coronal, sagittal and lambda sutures, they will fuse at the center. Then it will move on the right side and the left side. So we can determine the age. When we talk about sagittal suture, 30 to 40 years means they are all completely fused. Then we can say the suture is closed. It may be more than 40 years. Then we come to coronal sutures. Then we come to lambdoid suture. Means here we have to see. But when they are not lambdoid suture or coronal sutures are not totally fused, then we take the mid value. So we have to give the gap of 5 to 10 years. That's why it is given 30 to 40 years of the closing of sutures, because in every human skull the suture closes at different times. Another point, that now we have seen the suture from the outside of the skull. When we see through the foramen magnum, you will find the suture is also inside. It is very interesting to tell you that these sutures are fused first from inside. After 10 years, these sutures are fused. So there is a difference between 10 years of the closing of sutures from inside and the outside. Now you know this is the coronal suture, sagittal suture, lambdoid suture. Then we have another important point is there is these two. It is a saphenobasal suture. Now this suture is fused. When it is fused, it is more than 20 years of age. Now, in case we want to determine, so first we have to see the number of teeth. We know as a dental formula is a 2, 1, 2, 3, 32 teeth, the upper and the lower, then 2 incisors, 1 canine, 2 premolars and 3 molars. Now, in case the premolar or the molars are absent, it means it is not more than 30 years or 20 years of age, because the molar erupts at the age of 20 to 25 years, right? It again, it is a population characteristics. Then it is fused, and this saphenobasal suture is fused at the age of 20 years. So means here when suture is used is more than 20 years of age, and in that case we can determine the sex of the skull. If this suture is not fused, right, it means you cannot determine the sex because it shows the infantile characteristics. When we look at the parieto-mastoid suture. Now this is the parietal bone and this is the mastoid process. There is a confusion of the fusion of the two sutures. That's why it is a parieto-mastoidal suture. And then mastio-occipital sutures. Then we have the squamous sutures, right? And already I have told you saphenobasal. In some books you will find it is saphenobasal. Somewhere you will find it is a basal sutures. Now we will talk about secondary changes in skull. The first is texture. The texture of a young adult skull is smooth and ivorine on both surfaces. At about 40 plus minus 5 years, the skull surface begins to assume matted, regular and rough appearance. Markings on the skull after the age of 25 years onwards, the muscular markings become increasingly evident. The markings are temporal lines, nuchal lines, and gastric attachment on the site of mandible. After 50 years, the diploid becomes less vascular with increasing replacement of bone. The grooves for middle meningeal artery becomes deeper. The thickness of skull increases with age. The increase in thickness is more after 50 years up to 60 years with no decrease thereafter. Increase in skull size on lateral skull radiograph, Israel noted increase in skull size with increase in skull thickness and skull diameter with advancing age. Second comes age determination through tooth structure. When we talk about tooth, there are two types of teeth, primary teeth and secondary teeth, where you will find the diagram where we have incisors, canines, premolars and molars. So they are all the structure of these four types of teeth are different. Now we come to age determination through height and weight. Measurement of height gives idea regarding the individual of development of an individual. Average height is term employed, which means height of a person within range of permissible limits. That is, in other words, it lies between 3rd and 97th percentile of height, or within 2 standard deviations above or below the mean height of the age. The length of the child at birth is about 50 cm, 60 cm at 3 months, 70 cm at 9 months, and 73 to 75 cm at 1 year of extrauterine life. At the age of 2 years, the height is about 90 cm, and about 4.5 years, the height is about 100 cm. After that, the child gains about 5 cm in height every year up to 10 years of age. During the onset of puberty, there occurs growth spurt and add about 20 cm in height of a person. Thus, there is about 20 cm net increment in height of a person at puberty. Then becomes assessment of sex from skull. Now here, when we see the table, we can explain how we can explain the determination or assessment of sex. Now, assessment of sex from pelvis, hip bone or sacrum. The best bone for the determination of sex are those of the pelvis, which has an accuracy of 98% when properly examined. The pelvic bone, what also called innominate one portion, is composed of 3 bones, the pubic, the ischium and the ilium. Of these 3 bones, it is the pubic that is best utilized for the determination of sex. When we see, we can determine the pelvis as a whole in the male is more massive and has prominent muscle ridge. In the female, the pelvis is more slender, smaller and relatively smooth. The subpubic angle in the male is V-shaped with angle less than 90 degrees, usually about 70 degrees, that is the upper image, whereas the subpubic angle in the female is U-shaped, rounded, broader, divergent with an angle of 90 degree or higher. The body of the pubic bone, which is lateral to the symphysis, tends to be triangular in males, whereas in females it is more rectangular in females. Then there is a bony ridge running down the ventral surface from the pubic crest. In females, there is a concavity of the lower margin of the anterior pubic ramus immediately laid to the lower border of the symphysis. In female, there is a ridge of elevated bone on the medial aspects of the ischiopubic rami immediately later to the symphysis, whereas in males, this area is broad and flat. The ischiopubic index, that is the pubic length into 100 divided by ischial length, is less than 90 in adult white males. In adult females, it is over 95. The greater sciatic notch, this is the greater sciatic notch, in male is smaller, deeper and narrow, typically at an angle of less than 68 degrees, whereas in the female it is larger and more open, divergent, typically at an angle of 68 degree or greater. The obturator foramen is more wide in the male but triangular in the female. The preauricular sulcus, which serves for the attachment of anterior sacroiliac ligament, just lies lateral to the sacroiliac joint and is well defined in females but virtually absent in females. The sacrum in the male is typically longer, narrower and has a more evenly distributed, continuously curved the whole bone sometimes with a slight forward projection of the coccyx as compared to the female. In females, the sacrum is shorter, broader, with a prominent curve between S1, that is the hole 1 to 2, and S3. Also, the superior articular surface in males is larger than that of the females. The male sacrum may have more than 5 segments, which is rare in the female. The pelvic activity in males is relatively narrow and deep, whereas in females it is wide and shallow. The length of the ileum is greater than its height, making it to appear more vertical in the male, whereas in the female the ileum appears to be lower and to fillet outward. The pubic symphysis is higher in the males as compared to the females. Now I will tell you some of the important points or the name which we have discussed earlier on the pelvis. First is, this is the pubic symphysis. This is subpubic angle, which is very important to differentiate between the sex, between a male and female. In female, it is broad. In male, it is a narrow, because when the woman bears a child, the head of the baby comes out from here. That's why it is broad. And mostly this region is averted, opening outside, so that the head or the neck of the child, of the baby, is not get any marks on the body. Then we have this is the obturator foramen, right? It is different in male and female. Then we have a acetabulum, where the head of the femur articulates here. And means here, then there is a difference between the two male and females. Then when we go at, we say greater sciatic notch. Greater sciatic notch is broad in the case of male and is short in the case of female. Then we have the sacrum. Now their articular surface, the sacrum is more curved, right, in the case of male, and less curved, because we have to see again the ileum is very broad, because the weight of the baby is articulated or kept on this way. That's why it is a flat. Whereas in the case of males, it is elongated, right? It is not flat. Then we had other characteristics, because these are a few characteristics which one should know. This is the basic characteristics by which we can determine the sex. That's why when we say we get a pelvis, the best way is, in case we get a pelvis and a skull, we can determine with accuracy of more than 98% about the sex from the skeletal remains. In case we don't get skull and the pelvis and just we get the long bones, then the accuracy goes down, that it may be 60% or 70%. So in case we want to determine the sex or the age, the skull and the pelvis are the two very important skeletal remains. We can also determine the sex from other bones, and the other bones can be used to determine that are sternum, scapula and femur. The sternum is divided into two major parts, the upper and the manubrium, and the lower and the body, which comprised much of the sternum. The body in male is at least twice the length of the manubrium. It has less than this is in females. The scapula in males will generally have a deep suprascapular notch. That of the female is shallower. The vertical diameter of the glenoid cavity in female is less than 36 millimeter. In males, it is greater. Of the long bones, it is the femur which is mostly commonly used for sex determination. The femur in male is larger and heavier than in females. The angle of neck to the shaft is greater in females. Lastly, if the head diameter is less than 46 millimeter, it is generally female. The angle found by the neck of the femur with the shaft, that is called is colodiaphyseal angle is less than 40 degree in male and greater than 50 degree in the female. Now we come to see the demography in prehistoric population. Here I would like to say, before we go that, we can also determine the height from the long bones. We can determine the age, we can determine the sex, we can also determine the height of the individual from the long bones or different bones which are prevalent or which we found from different areas. Now I will tell you a very simple method, that is, in case we take the total length of the female and multiply with the multiplication factor. Each bone has a different multiplication factor, so we get the estimated stature of the individual. The demography in prehistoric population, the likely approximate size of this first human population was near about 100,000, probably already divided into distinct groups. They emerged as the earth was entering an ice age, which, like any climatic change, resulted in the disappearance of many species and the emergence of new ones. Homo habilis disappeared as Homo ergaster emerged, spreading throughout Africa and thence across Europe and Asia in the form close to Homo erectus. The standard method for estimating prehistoric population distribution is to attribute to a given area the population density recorded in a recent period among people of a similar culture living in a similar environment and climate. In the Paleolithic area, population distribution was more closely linked to the size of territory populated and to climatic variations than to the still very primitive technology. It is therefore remained very sparse despite all technical leaps like learning to control fire. The total number of Homo ergaster and Homo erectus may be very roughly estimated at between 500,000 years and 700,000 years in the Old World, that is Eurasia and Africa, which were the only populated areas at the time. Then between 300,000 and 200,000 BCE, that is before Christian and Common Era, three distinct hominid population groups developed at the same time but far apart, separated by the oceanic rise in the last two interglacial periods. That is the modern man, that is Homo sapiens in Africa and southern Asia, perhaps 800,000 individuals, the Neanderthal man in Europe, perhaps near about 250,000 years, and Java man in the Indonesia, perhaps 100,000, with the last ice flood around 70,000 BCE. Falling sea levels brought the three hominid population groups into contact. Homo sapiens asserted his supremacy everywhere, squeezing out first Java man, then Neanderthal man, and spreading between 50,000 and 40,000 BCE across the as yet unpopulated continental land masses. Australia, the two Americas, and later on Siberia. The world population at this time may have totaled near about 1.5 million, including 1 million in Africa and Asia, 50,000 in Australia, 300,000 in America, and 150 in Europe. The later two continents being still largely under ice around 40,000 BCE. Technological progress in the form of invention of the spear thrower, the harpoon, the bow, and arrow vastly improved the efficiency of hunting and fishing and became the main engine of population growth, especially in Europe. Taking advantage of the falling sea level, which greatly narrowed the strait between Sicily and Tunisia, two waves of Europeans migrated to North America around 20,000 BCE and 12,000 BCE. They populated it from the Canaries to Egypt, stretching even as far as Arabia, At the height of the late Paleolithic age, from 10,000 to 9,000 BCE, the population of Europe may have stood at 200,000 people. The sudden climatic warming, which occurred around 8650 BCE, halted their growth, and the beginning of the Mesolithic era saw the population decrease, then increase rapidly with a cultural adaptation to the new climate and the repopulation of northern Europe as the ice melted. Around 7000 BCE, it is likely that Europe had close to 400,000 inhabitants, with the Neolithic era in the Middle East. From 10,000 to 8,000 BCE came sedentaries, hand hook cropping, stock rearing, pottery making, and navigation, resulting in a tenfold increase in the population from 0.5 to 5 million inhabitants. From Anatolia, Neolithic people migrated to Greece, settling near what would become Thessaloniki, and from this densely populated settlement sent out two streams that propagated Neolithic culture in Europe. One sea-borne, investing the coastal region as far as England, the other across land, moving up the Danube to occupy the central part of continent. By around 4000 BCE, the Neolithic culture has spread across Europe with a population of perhaps 2 million, rising so rapidly that it could well have topped 23 million by around 2000 BCE, when the advent of the Bronze Age brought a population decline. In Indian context, Neolithic culture first emerged there in the Punjab, which also rapidly developed into major population center, rising from perhaps 0.7 to 20 million between 4000 and 2000 BCE. From 8000 BCE, a Neolithic culture also developed in the Huanghe River basin, now it is in China, extending towards the east and then the south, where corn gave way to rice. Here again, the population rose from 0.8 to 20 million between 4000 and 2000 BCE. Other Neolithic civilizations developed somewhat later in Mexico and on the higher plateaus of the Andes, likewise bringing a population surge. Finally, other partial civilizations developed around pottery and primitive farming for 12,000 BCE in Japan and 8,500 BCE in African Sahel. When we come to population size, a disparate range of archaeological evidence, including the number and the size of houses within settlements, the areal extent of settlements, the economic potential of the catchment areas around population centers, and various measures of the exploitation, consumption, and discard of raw materials and artifacts can be used as proxies for estimating population size and density. For example, Beckett, Appel, and team modeled populations sizes in Upper Paleolithic Europe using the spatial density of archaeological sites, a proxy measure of population density, combined with numerical estimates of population density taken from ethnographic studies of North American forages who lived under similar bioclimatic conditions to those experienced in Europe during the late glacial period. By assuming that the average population density derived from the ethnographic data represented the carrying capacity of the late glacial environment, that is the maximum population density for the European late glacial period, they were able to convert their archaeological data into estimates of actual population density from which population size and growth over time could be modeled. Measures of relative population size based on artifact discard rates who have also been used to determine correlation between large-scale environmental changes and hominin population density during the Middle and Upper Pleistocene in Britain. Horsfield and Aston and Levi's identified relative changes in human population density in the late Middle Pleistocene Britain by quantifying the density of accumulation of bifacial stone tools in gravel terraces in southern Britain from oxygen ausotype stages 13 to 2, a period of approximately 500,000 years. Their calculations take into account the spatial extent of commercial minerals extraction and urban development in the study areas. That is, two of the principal factors affecting the archaeological data through their influence on the discovery potential of stone artifacts. The result of these studies indicate a sharp decline in evidence for human activity in the Middle Thames Valley after 350,000 years ago. Although 100 kilometers to the south, in the area surrounding the former Solent River, the population appeared to increase during late OIS 9, suggesting some regional variations in population processes during this time period. Now we come to population growth. The increasingly large data sets compiled from radiocarbon dating programs provide an index of changes through time in human population density, an approach that has been used to ascertain the timing of the extinction of Neanderthal population and the subsequent colonization and recolonization of Europe by modern humans during the late Pleistocene. A useful application of spatial database of radiocarbon date is to determine the rates of spread of demographic waves of advance during continental scale periods of colonization and culture change. The proxy data on population numbers provided by radiocarbon dating can be combined with the estimates of fertility and migration in the construction of colonization models. The rate of advance of Paleolithic hunter-gatherer populations re-entering Northwest Europe after the last glacial maximum have been estimated to be 0.5 to 2 km per year, values that are similar to those established for the spread of early farming. The higher migration rates of foragers presumably compensate for their lower fertility and lower intergeneration intervals, which would otherwise demographic expansion rates. Then comes to age at death, that is the distribution and mortality patterns, the levels and the age distribution of mortality, that is the mortality profiles for past population have been reconstructed through the application of life table methods and or hazards modeling to age-death distribution estimated from assemblage of human skeleton remains. Such approaches rely on the use of skeleton indicators of growth and census that shows consistent correlation with age at death across samples and population. Traditional anthropological methods for estimating age at death from the skeleton have typically used measure of the central tendency of age for particular skeleton indicators, or those methods have relied on regression of age on skeleton indicator state, the so-called inverse regression, to predict age at death in cemetery populations. The short-term potential for human population growth in small populations is often high, with instantaneous population growth rates between 0.5% and 2% per year documented for hunter-gatherer groups such as Achi, Agata, Asmat, Hadza, and Yanomama from South America. However, estimates of long-term population growth rates based on historical and archaeological data are typically much closer to zero, suggesting that episodes of catastrophic mortality that cause substantial losses to living populations and that occur every few generations may account for the balance between short-term and long-term population growth. Now comes to fertility. Unlike mortality, which frequently leaves an archaeological signature in the form of skeleton remains accompanied by evidence of funerary ritual, fertility is much less visible in the archaeological record, and estimates of fertility are usually derived indirectly from measures of mortality and population growth. The material traces of the birth processes are ephemeral in the archaeological record. Birth events do not often result in recognizable deposition event, and neonatal mortality especially is often underrepresented in mortuary assemblages. Variations in fertility can be investigated indirectly through their effects on the age distribution of deaths and simple paleo-demographic measures that is responsive to fertility is the juvenility index, in which the number of deaths of older children are expressed as a ratio of their deaths to the number of adult deaths in the population. The deaths of infants and younger children are excluded from the calculation of the juvenility index to avoid the biasing effects of differential mortuary practices and post-deposition preservation of potential that adversely affect the proportion of these age categories in skeleton samples. As fertility is closely correlated with overall mortality, the juvenility index is regarded as a suitable proxy for estimating fertility in past populations. In communities practicing agriculture, female total fertility is on an average higher than that in foraging populations, with age-specific female fertility peaking in the early 20s rather than in the late 20s or early 30s. As observed in the foraging populations, annual birth rates are generally higher at all maternal age in agriculturists. Lifespan, a key challenge for archaeological demographers, especially for those studying prehistoric population, is to determine the extent to which uniformitarian models can be applied in paleodemography. From research in human life history variables, it is apparent that milestones in both development and senescence, such as age at weaning, age at reproductive maturation, the timing of female fertility decline, and the maximum potential lifespan, are subject to stabilizing selection and relatively invariant across present-day human population. Some life history variables, that is, fertility and longevity, are difficult to measure in past populations, but while one life history related feature of skeleton development that provides a reliable chronological marker in both extant and fossil species is the time taken for the crowns of teeth to form before the teeth erupts into the mouth. Studies of the chronology of tooth development based on counting of increment growth markers in dental animal have shown that fossil hominin species achieved dental maturity in approximately 2/3 the time that modern humans require to reach an equivalent development stage. In addition, modern human tooth formation times appear to have been established more than 150,000 years ago in the earliest representative of anatomically modern sapiens. Because life history variables are strongly intercorrelated, at least at the level of species comparisons, the distinct pattern of delayed maturation that is characteristics of anatomically modern Homo sapien is expected to be accompanied by increased longevity and maximum lifespan. The estimation of longevity in fossil hominins is not straightforward because, unlike the situation with animal growth, adult age at death is not directly measurable and must be inferred from skeleton indicators that have only an imprecise correlation with the chronological age of the individual. Maximum potential life span in great apes appear to be between 50 to 60 years and 60 years, with wild individuals exhibiting physical and behavioral signs of senescence from their mid-30s onwards. At the same stage in human evolutionary lineage, a delayed onset of senescence and extension of longevity appear to have evolved, perhaps concurrently with the extended period of maturation evident from the record of dental development. Kaspari and Lee investigated the evolution of human longevity by calculating the ratio of older to younger adults in samples of fossil hominins belonging to genera Australopithecus and Homo. older adults were defined as those individuals estimated from dental wear to be more than twice the age at which skeletal maturity was achieved, and determined that proportion of older adult individuals in their fossil species samples increased from 10% in Australopithecus to 20% in early Homo and 28% in Homo neanderthalensis. In contrast, a much higher proportion of older adults, that is the modern human values of about 70%, was found in the samples of European early Paleolithic Homo sapiens. Now we talk about life tables. First, modern life tables calculated for wild populations of chimpanzees, what we call is pan-troglodytes, shows that these apes have a attritional mortality pattern in which most adult deaths fall into the older adult category. The Pliocene-Pleistocene assemblage of Homo habilis from Old George, the late Pleistocene sample of Homo heidelbergensis from Cima de los Osos in Spain, and the Homo neanderthalensis specimen from Krapina in Croatia are all dominated by high proportions of adolescent individuals, that is 30 to 60% of these samples. Adolescents constitute the age category least expected to be present in attritional mortality assemblage because they represent the age at which risk of death is minimized in modern life tables. The presence of adolescents in the hominin mortuary assemblage is actually a signature of catastrophic mortality, as the adolescent age category forms a substantial proportion of the living population. The distinctive hominin patterns of excess adolescent and young adult mortality is predicted if prediction, that is either by large carnivorous in the case of early hominin species or through inter and interspecific violence in the case of later species of Homo, made a significant contribution to the formation of fossil hominin assemblages. Both large carnivores and human hunter-gatherers commonly use hunting methods that select prey in proportion to encounter rates, a practice that generates age distribution in the prey assemblages that mirror the living age structure of the prey population. The module can be summarized as, due to its resistance to decomposition, the human skeleton proves to be an extremely valuable source for the reconstruction of past life parameters. The prehistoric sample displays complex biological variation and evolution of prehistoric inhabitants, possesses general skeleton biology, facilitates synthetic review of biological temporal trends, and suggests a general temporal increase in certain pathological conditions and other indicators of population stress. Due to its resistance to decomposition, the human skeleton proves to be an extremely valuable source for the reconstruction of past life parameters. These death structures serve as indicators of overall life expectancy, fertility, and even population growth. Moreover, historical patterns of health, disease, and ontogenesis are used to isolate biological as well as social life history factors. A demographic study of a skeleton sample begins with the assessment of both the age and death and sex distribution of the skeleton material. A disparate range of archaeological evidence, including the number and the sizes of houses within settlements, the areal extent of settlements, the economic potential of the catchment areas around population centers, and various measures of the exploitation, consumption, and discard of raw materials and artifacts can be used as proxies for estimating population size and density. the distinctive hominin pattern of excess adolescent and young adult mortality is predicted if prediction either by large carnivores in the case of early hominin species or through inter- and intraspecific variants in the case of later species of Homo made a significant contribution to the formation of the hominin assemblages. Thank you.